Welcome back, everyone. In this video, we will be continuing the L'Hopital's rule or indeterminate form section. Now, in the previous video, we talked about how there's really 7 indeterminate forms. They fall into 4 categories, but the one category works directly with L'Hopital's rule, and that's if we get infinity over infinity or 0 over 0. But anytime we want to do a limit, we want to block out doing anything besides plug it in right away. But what do we want to do if we want to do the limit as x goes to infinity of the natural log of x squared over x cubed? Keep in mind this squared is on the outside of the natural log. It's not inside the x, so it won't come in front. Then we just need to plug in infinity and see what happens. Now remember, we can't really plug in infinity ever. So when we say plug in, it's really in quotes, because we're doing the limit. If it was 0, we could just plug in 0 and see what happens. But for plugging in as far as infinity goes, we can't really do that. So the idea is, if you want to be extremely proper, you do the limit of the top, the limit of the bottom, and both of these will follow from a couple of the reminders I gave you above. The limit as x goes to infinity of a positive power of x is infinity. And the limit as x goes to infinity of the natural log of x is infinity. When you square infinity, you still get infinity. So technically, this looks like infinity squared because the limit part for the natural log of x to infinity is infinity. But when you square a really big number, it stays really big. So I'm going to go ahead and just get rid of that. And we've checked that this is an indeterminate form. It's already in the proper form for L'Hopital's rule. So we can go ahead and use L'Hopital's rule. So exactly like last time, I'm going to start by just rewriting it. We got the limit as x goes to infinity of what we want to do, the limit natural log of x all squared over x cubed. And L'Hopital's rule, which I'm going to write over this equal sign like I did last time, says do the limit to the same value, but I want to do the derivative of the top and the derivative of the bottom. So the derivative of the top, well, this is going to involve the chain rule because we have something squared. So we bring the power down, rewrite the inside, which is the natural log of x. We would rewrite or minus 1 from the power, which is just 1. So I'm going to leave that off. And then we multiply by the derivative of the inside. And the derivative of the natural log of x is 1 over x. And then this is over the derivative of x cubed, which is 3x squared. Now, before I go ahead and plug in again, because this is a little messy, I want to simplify it. And we have the 2 natural log of x times 1, which is 2 natural log of x on the top. But because this x is on the bottom, we can just shove it down here with 3x squared. Because this is the bottom, we can just bring it down. And it will become 3x cubed. All right, if this was just x instead of 1 over x, then the x would be on the top, and we could do some canceling to simplify. But this one's on the bottom, so it goes with the denominator. Right. Now, what we've done here is we simplified after L'Hopital's rule. And sort of like before we talked about L'Hopital's rule, but we were doing limits, we would always want to try to simplify if we got an indeterminate form and then plug back in. So the idea is now plug it in again. All right, so we go ahead and we plug it in again. We're plugging in the same number, infinity. So we can't really plug it in, but when we plug it into the top, well, we know the limit as x goes to infinity, the natural log of x is infinity. We multiply it by 2, it's still infinity. And if we go to the bottom, we plug it in and we get 3 times infinity because it's a positive power of x, which is just infinity as well. So this is infinity over infinity. And once again, we have to use L'Hopital's rule. All right, and just like last time, we want to use it from where we already implemented the first L'Hopital's rule. We don't want to start from the beginning and just do the same thing twice. we'll just build on this. Now make sure you go ahead and do it from this simplified spot. Okay, don't do it from this right here, because when you do the derivative from here, it's just going to be messier. You simplified it. It's a lot easier just to do the derivatives from L'Hopital's rule from this one. So that's where we'll take it from. We're going to do the limit as x goes to infinity of, I'm going to rewrite where we were at, 2 ln of x over 3x cubed. And L'Hopital's rule says do the derivative of the top and bottom. The derivative of 2 times natural log of x, this would be 2 times 1 over x over 3, and then the derivative of x cubed would be 3x squared. We got the limit as x goes to infinity. We did our L'Hopital's rule. Now we simplify. Just like with the previous one with the 1 over x on top, we can bring the x down to the bottom, and we're just left with 2 on the top. And on the bottom we have 9 from the 3 times 3 and x squared, but it's really x cubed because the x comes down there. So it's 2 over 9x cubed. And now what we can do is plug in infinity again. We simplified it. Now plug it in. And we get 2 over 9 times the limit as x goes to infinity of x cubed is infinity. So this is really 2 on the top and infinity on the bottom. And hopefully the thing you remember is that a number over infinity, this is not indeterminate form, this is 0. So just a reminder, a number that's not infinity over 0 equals, or sorry, a number over infinity equals 0. And that's it. Yeah, we had to use L'Hopital's rule twice, just like with the first one, but the idea is we can do a limit now that before L'Hopital's rule, this was impossible, because with this thing, yeah, we could see it's infinity over infinity, but the only methods we had to simplify before was divide by the biggest power of x or factor and cancel. We had nothing we could possibly factor and cancel from the original. So our answer here is 0. Right. And then number 3. So number 3, we're doing the limit as x goes to 0 of sine of x plus x to the 4th over x to the 6th. Right. Let's see what happens here. Well, what we want to do, usually functions are given to us pretty simplified. There's nothing to possibly factor and cancel out. So let's go ahead and plug in 0. And the nice thing about 0 is we know we can just plug that in. We get sine of 0 plus 0 to the 4th is 0 over 0 to the 6th, which is 0. And sine of 0 is also 0. So this is 0 over 0. And this is in an indeterminate form that we can do L'Hopital's rule again. And L'Hopital's rule says, well, let's go ahead and do derivatives. So limit, I'm going to do what I've been doing, rewrite it. We have the limit as x goes to 0 of sine of x plus x to the 4th over x to the 6th equals, and then L'Hopital's rule says, well, oops, I switched to infinity by mistake, 0. We want to go ahead and do the derivative of the top, do the derivative of the bottom separately, and see what happens. So we got 6x to the 5th just for the bottom's derivative. The top, the derivative of sine of x is cosine of x plus, and the derivative of x to the 4th is 4x cubed. All right. So we've implemented L'Hopital's rule. Now we want to go ahead and plug it in. And when we plug in 0, we get cosine of 0 plus 4x cubed. Well, that's, if we plug in 0, we get 0 over 6x to the 5th, which is also 0. Well, cosine of 0 is not 0. So we are not going to be in an indeterminate form anymore, because this is 1 plus 0 over 0, which is 1 over 0. And one of the other things when we're talking about limits at infinity, infinite limits, is that a number over 0, as long as the top's not 0, is plus or minus infinity. All right, but as far as doing the limit when we get 1 over 0 is, it might not exist. It might be infinity. It might be negative infinity. So what we have to do is we have to check the one-sided limits. And we want to check the one-sided limits to see if the limit is infinity, negative infinity, or D and E. Because the one-sided limits might be the same. And if they're the same, it's going to be one of these. If the one-sided limits are different, then it's going to be one of these. Now, as far as checking the one-sided limits, we don't actually go through and do L'Hopital's rule again because we're just going to do the same thing with like a plus or a minus here. The thing you want to remember is we plug in numbers. So if I want to do the limit as x goes to 0 from the left of our original limit, sine of x plus x to the 4th over x to the 6th, we don't go through and do L'Hopital's rule again, even though we could, because we'll just end up in the same spot here. What we do is we plug in a number that's a little to the left of 0. So let's say we plug in sine of 0.001 plus 0.001 to the 4th over 0.001 to the 6th. Now what you want to notice here is when I'm plugging this number in, I am plugging it in to the original limit. And the basic reason for that is when I plug in a number that's close to 0, I'm not actually doing a limit. I'd have to plug in another number and another number and another number. So L'Hopital's rule really narrowed it down for us into 3 possible options. And now we're using the one-sided limits to know which of those 3 options it is. All right, but just a reminder why I'm plugging in this number. Actually, I need to plug in a negative one because I'm to the left. So my apologies there. We want to plug in a number that's close to 0, but negative, smaller than it. And, pretty much you can't really avoid using a calculator for one of these, but we want to try to refrain from looking at the graph while we do this, because the graph is going to tell us, and we want to understand the entire analytic process. So just we'll type this in, sine of negative 0.001 plus negative 0.001 raised to the 4th, all divided by negative 0.001 raised to the 6th. Go ahead and hit enter. Make sure you're in radians, which we are. And the point of the result here is that it's a really big negative number. So what you want to remember from way back when is that when we plug in a number, when we know the limit is infinite like this, if we get a negative one, then it's negative infinity. If we get a positive one, it's positive infinity. So this is going to be negative infinity. Go ahead and write that in. And then when we do the limit coming from the right, we're going to plug in a number close to 0 again, but it's just going to be positive. So when we do the limit as x goes to 0 from the right of our original function, I'm pretty much going to plug in the same thing but positive. 0.001 plus 0.001 to the 4th over 0.001 to the 6th. So that's a number greater than 0 and close. And if you use this calculator just to do this type of problem, then you can just get rid of the negatives. But if you have it all typed in your own calculator, you can just get rid of the negatives there, press enter. And we see that this is actually positive. It's 1 times 10 to the 15th, so it's going to be positive infinity. And since the one-sided limits are different, that means that this is D and E. Now, one thing we can go ahead and add in, it may be in this problem, you're asked the same exact problem, but you're only asked the one-sided limit at the beginning. Well, that means that if you're asked the limit as it comes to 0 from the left, then you would just do this part and get this number. but different one-side limits because we wanted the entire limit here is giving us a D and E for our answer. And I thought that problem would be a good reminder because we only had to do L'Hopital's rule once, but it didn't give us the final answer. We had to do a little bit more. Now, one thing I want to do real quickly on this problem is just show you the graph of this and then the graph of after we did L'Hopital's rule. You're going to notice that they're very similar, but they are slightly different, which means that when you do this step here, when you're plugging in numbers close to 0, you're not getting necessarily an accurate number when you plug it into the one where you did the limit. And, you know, most problems, it might not throw off your sign. So, you know, if we plugged in negative 0.001 to this instead of the original, we'll probably still get a negative number. But you don't know if what you're plugging in is necessarily close enough for the new function, basically. So you have to be careful. And our original function is the one in green. You can see as we come towards 0 from the left, we go to negative infinity. As we come towards 0 from the right, we go to positive infinity. And that's exactly what we got. Now with the limit of the new function, after we did L'Hopital's rule, I have that graphed in purple, and it's the same thing. But you'll notice that it is a little off, right? So it's not the same exact function, which means, you know, what if I thought, well, maybe what if I think just plugging in x is 1 is good enough? Well, if I plug in x is 1, then the problem is you can kind of see right here, this is where x equals 1. For this one, it's definitely a positive number, or negative 1, sorry, the y value. Now we should know that plugging in x is negative 1 is not close enough to 0. We have to really get close with the decimal numbers. But even if I plugged in like 1/2, you can see that at 1/2, which is this line here, the green one is way down here. The purple one is barely negative. And we probably can't say, well, the y value is negative 1, so it's going to be negative infinity. So the main point here is that it might work if you plug it into this one, but it will definitely work if you plug it into the original. So make sure you're doing that. All right, so I think this is a good place to stop. In the next video, what we'll be doing is looking at problems where we have to use some technique to get it into the correct indeterminate form. So the last 3 problems in this section that I'm going to show you will either be a difference or a product or one of those exponential ones, and we'll talk about the technique to getting them into the correct indeterminate form, and I'll see you there.